Okay. So the Mobius inversion formula, if you recall in the last lecture, we saw the function zeta, which was defined as zeta of tu for any closed interval tu to be 1 whenever t was less than equal to 1, less than equal to u, right? So basically, zeta takes value 1 for any closed interval, any non-empty closed interval.
Yes.
Okay, and we said that empty cannot be realized as a closed interval.
Yes.
So that was the setup we were working in. And since zeta was non-zero for any value, we also saw that zeta is invertible, right? By that proposition which we saw in the last lecture,
Yes.
where we had an equivalence of 2-3 statements.
Yes, ma'am.
So its inverse is exactly the function which we call as Mobius function of that particular poset. Okay, and we denote this by mu.
Okay.
Right? So since you call this as inverse of zeta, it's same as writing mu zeta equals to delta, where delta is the identity function.
Yes.
Okay, on any interval. However, if you remember, mu zeta now written as a product, you apply the convolution on it. So
Yes,
this can independently be derived, and you would arrive at this, that mu of su is 1 when s is equal to u. So when you apply convolution on it, you will take any interval su, let's say, so delta of su. Now delta of su is 1 if and only if s is equal to u, correct?
Yes, ma'am.
And on this side, mu zeta of su is actually summation of mu st zeta tu, with t lying between s and u, right?
Yes, ma'am.
So when you expand this entire thing for the chain S, or not really the chain, there could be more than one element. So S is the smallest element, let's say, in this poset, and T is the largest element, U is the largest element in this poset. And now you look at all the elements T which are in between S and U. So when T hits, so when U is equal to S is when this function also evaluates to 1, and this also evaluates to 1. Therefore, mu of this becomes 1 when S is equal to U. For all other values, which means any other T in between of S and U, which is strictly bigger than S. Okay, for all those values, what you would have, you will have a mu of ST and zeta of tu with
Yes.
t less than u. But zeta of tu for any such t and u is equal to
1.
1. And this is equal to
That will be 0.
0. So what you're left with is that mu of st is equal to 0. The entire summation is equal to 0. From that, you extract out the mu su, and therefore it can be written as mu of su is exactly equal to negative of the summation mu of st, where t is strictly between s and u. Okay, now t cannot hit u because this particular thing you have taken out here.
Yes.
Okay, and this is valid when s is strictly less than u, because s equal to u, it evaluates to 1.
Yes.
So this equation actually gives you this definition for the Mobius function. Okay, now we have the theorem which, so it's an inversion formula, right? So sometime back when we were dealing with elements where we tried expressing one function in terms of the other, and that went both ways. So remember how we had alpha and beta?
Yes, ma'am.
We wrote alpha nt in terms of beta nt and beta nt in terms of alpha nt. Similarly, we had some f equal to of t, and we expressed it in terms of f greater than equal to of t, and vice versa. And
Yes,
same happened for f less than equal to of t, expressed in forms of f equal to of t. Right? So inversion
yes, ma'am.
formula again here in some sense says how you can express one function in form of the other one. So what gets inverted is what you have to see. But before that, a little, so to say, some notations from the poset theory. So if you have a poset P and you take a subset I, then you call this subset I to be an order ideal if in the most natural sense in your head, it is an ideal in the sense of algebra, which means that if you take any T, and since it is order ideal, you take all the elements which are less than equal to of that element. So if some element T is there in the set I, and you take any element which is smaller than T, then this S has to be in the set I. Okay.
Yes, ma'am.
So this is the definition of order ideal. And now how you, I think I did not define the word chain, but chain just means that you start with an element S, and then let's say you start with S0, then S0 less than equal to S1, less than equal to S2, less than equal to S3, and so on, less than equal to Sn till. So then this is a chain. So
Yes, ma'am.
totally ordered subset of a poset. Okay. So if you pick any two elements, they are comparable. So if you take any such subset of your poset, that's called a chain. All right.
Okay.
In contrast to a chain, you have an anti-chain, which means you take any two elements of this subset, they are not comparable. So in chain, any two elements are comparable. In anti-chain, it is anti of the chain. So no two elements are comparable. Totally incomparable elements form an anti-chain. Completely comparable elements forms a chain. Okay. So what really is an order ideal? Order ideal is taking any element T and then collecting all its smaller elements. Which means if you look at I and you consider the elements of I which are non-comparable, okay?
Yes.
So in some sense, you form the chains which are available in your set I, and then you pick up their largest element, max element in each of these chains, and you take those elements and form a set, then that is a anti-chain.
Yes, ma'am.
Why? Because if you have taken any two elements from this set, they are incomparable. If they were comparable, then one of them would be smaller than the other one. But we said that we have collected all the maximal elements, right?
Yes.
So any order ideal can also be can also be interpreted and written as I is equal to the collection of those elements of a poset which are less than equal to T, or rather which are less than equal to some element of an anti-chain for some particular anti-chain A. Okay.
Okay.
So for every I, there is a unique A, and every A determines a unique I. All right.
Yes, ma'am.
So if A has, let's say, k elements T1, T2, Tk, you also write this thing in the fashion I is equal to T1, T2, Tk with these brackets, left angle, right angle. And you say that I is generated by the elements of A, which are the K, T1, T2, Tk. Okay. If the antichain happens to be just one element, then you say that I is generated by just this element T, and you denote this. This is called a principal order ideal in this case, and it is denoted by gamma T. Okay.
Okay, ma'am.
So now you understand what a principal order ideal is. With this in picture, we can see the Mobius inversion formula. So this theorem states that if you take any poset P for which every principal order ideal is finite, so this also needs to be finite. See, now I have actually dropped that P has a um,
Locally finite.
yeah, and actually that does not even if P is locally finite, that does not tell me that gamma T has to be finite.
Yes, ma'am.
Because each gamma is much more than just an interval. Right? So if you take two functions f and g from the poset to k, then function gt is expressed as a summation of fs for s less than equal to t, if and only if the function f can be expressed as f of t equals summation of gs mu of st. So you see the sort of convolution is coming into the picture, or rather you say that mu acts on G from right.
Yes, ma'am.
Okay. So yeah, with this in the picture, so this one we'll see a quick proof, and the other, I mean, there is a dual form of this. That proof we'll leave because it follows similarly. Excuse me. So sigma, if I start with this sigma gs mu st s less than equal to t and substitute the value of gs, okay, so then this, assuming this is equal to summation of fu u less than equal to s, right? That's what it is evaluated to, and
Yes.
mu of st. But now this particular function and this are independent of u. So you take u out, and then you had the restriction of less than equal to s, which is then further restricted by s less than equal to t. So you have summation u less than equal to t of fu times summation mu of st with u less than equal to s less than equal to t. Correct? But what is this really? Mu of st of with u less than equal to s less than equal to t. It's just the delta of ut.
Yes, ma'am.
It will
By
survive
the inverse thing, right? No?
the other side. This one.
Ah,
It
yes, ma'am.
survives on, I mean, this one really cancels out, so only this survives.
Yeah.
Where am I? Here. So this is delta of ut, and then fu of delta ut summation u less than equal to t was f of t. This is something which we saw, I think, 2 lectures back, when we said that any function f will be treated in this way.
Yes, ma'am.
Yeah. So just before the proposition which said the f has a left inverse if and only if it has a right inverse, if and only if it has a two-sided inverse, if and only if ftt is non-zero for every t. Just before that, we had stated that f in the incidence algebra IP is identified with the expression f is equal to summation of f of st on the interval st. Okay.
Yes, ma'am.
So this becomes the value ft. Therefore, the two statements are equivalent. Here, if you see, we dealt with the principal order ideal, and the order ideal is defined when you take elements which are smaller than the elements in this. So it's like you are collecting all the shades or shadows. Which way is it? You're collecting the downward elements, basically.
Yes, ma'am.
Okay. So dual to this, you can have something when you collect upper elements from a particular element.
Yes, ma'am.
So starting with an element, let's say t in some subset, let's say I prime, you would then want to collect all those s which are greater than equal to t. Okay. And
Yes, ma'am.
those elements also you would want to put in the I prime. So there is indeed a notation for that. That is called a dual order ideal. And then you have the same anti-chain concept, and you build the anti-chain in the upward manner then. From the anti-chain, you build the dual order ideal in the upward fashion. So you collect the elements of the anti-chain. Now, the minimal elements of the totally ordered chains, right?
Yes, ma'am.
So this entire notation which we saw is dualized. You will have that I prime is the collection of all those elements of T which are greater than equal to some element of that particular antichain. Correct?
Yes,
And
ma'am.
similarly, you would have the notation that given the antichain T1, T2, Tk, you would write I prime to be generated in some fashion. Okay. And if this is having a cardinality 1, then it is a principal dual order ideal. Okay. So that is what we see now. So principal dual order ideal generated by T is Vt, which collects all the elements S which are greater than equal to T. Okay, so I've cut short all the notation here because all this is actually not needed, right? What I needed was just the principal order ideal even here. And I could have said that principal order ideal gamma T is the collection of all S in P such that S is less than equal to T. The definition could have ended here for gamma T, right?
Yes, ma'am.
And similarly, now we have the principal dual order ideal. And for that, the dual order ideal Vt has all the S in P such that S is greater than equal to T. And for the principal dual order ideal, we have a dual form of the Mobius inversion formula, which says that if P is a poset such that Vt is finite for every T, and f and g are two functions from P to K, then g of s is summation of ft for every summation taken over all s less than equal to t, if and only if f of s can be represented as summation of mu of stgt. Again, s is less than equal to t. And you define both the definitions g and s, g and f, both remain valid for every value s of p. Okay, proof is pretty much similar. Only thing you notice now here is that now mu of st acts on the function g from left.
Yes, ma'am.
But what is the use of these? So use is that when you really want to compute the Mobius functions, then you see the equivalence of these formulas. So I will give one, yeah, I will give one particular instance, and then more you can read from the book itself. 1 second. Where did this go? Yeah, can you see?
The third page of the lecture.
Yeah, third page, right?
Yes, ma'am.
So we now see techniques for computing these Mobius functions. So if you let P to be the chain N, so first of all, are you convinced that P is a chain if it is N? So you have the uh, binary operation, I mean the what to say, the partial order
Yes, ma'am.
as the order on the set of natural numbers, then P is indeed a chain. And
Ye-
furthermore, if you look at this particular theorem, sorry, here. So it's a poset for which every principal order ideal is finite. That is needed.
Yes, ma'am.
So is that true here? If
Yes,
P
ma'am.
is n, then every principal order ideal is finite. However, can a principal dual order ideal be finite here?
No, ma'am.
No. Although P is locally finite.
Yes, ma'am. Correct.
You see? So
Yes, ma'am.
that's what I was trying to say that time. Even if I mean, this entire theory, I have to anyway assume that P is locally finite, because otherwise I do not know how to deal with the intervals. All
Yes.
this business still is happening over the set of intervals, int P, right?
Yes, ma'am.
But see this. So if P is the chain N, then the mu of ij, remember mu of ij was 1 when I was equal to j very clearly, and it was summation of, it was negative of summation of mu of I u, where u was strictly less than j.
Yes, ma'am.
So for all other values, again it would vanish, and the only one where it survives really is the value when it is just one level up. So when j is I plus 1, so you are actually computing mu I plus 1. Sorry, mu I comma I plus 1. So that becomes minus 1, and rest otherwise everywhere it is 0. Okay,
Yes.
maybe I need to share another page for you to understand this. It's clear, right? Okay,
This is the first definition we saw, right?
right,
Using the.
right, right. This here,
Yes, ma'am.
yeah. So, so then the Mobius inversion formula takes the form g of n is equal to summation of fi, I lying between 0 and n. Okay, so I is greater than equal to 0 and going up till n. So this is the first side, right?
Yes, ma'am.
You're working with the principal order ideal. So this is the one you would hit. So g of this is equal to summation f of s less than equal to t. So g of n would be s less than equal to n f of s. Right? That's what I have written as s from 0 to n f of s. Right? Or f of I from 0 to n. And then this is equivalent to f of t to be equal to summation g of s mu of st, s less than equal to t. So come here, f of n is g of s mu of sn, s less than equal to n, which means s is from 0 to n. Okay.
Yes, ma'am.
Now, if I evaluate this entire thing, I know that this is going to survive when mu is non-zero. And mu is non-zero only for two values. So since n is fixed for me every time, the only values when mu is non-zero with respect to this particular parameter here is mu n minus 1 n and mu n n, right?
Yes, ma'am.
And mu n minus 1 n evaluates to -1, mu n n evaluates to 1. What is the coefficient of mu n minus 1 n? It is g of n minus 1, and mu of n n comes with g of n. So what you actually get is that g of n minus g of n minus 1. So fn is gn minus gn minus 1. Okay. So gn is equal to this particular summation if and only if fn is equal to gn minus gn minus 1. Okay. But here we were we were lucky because we could see the Mobius function very clearly, right? The structure on n is very nice, so you could figure out very quickly what mu would be. But that may not always be the case. So for such instances, we need more data, or rather more stronger techniques to figure out what a Mobius function would be. So in that direction, we have a product theorem which lets us compute Mobius functions for one next step. So it's just how from posets you will have subposets or product of posets, etc. This tells me if I can figure out the Mobius function for some particular posets and the other poset can be, interpreted as a product of two posets, then the Mobius function, this theorem tells me how to compute the Mobius function for this product of two posets. Okay. So before
Yes, ma'am.
that, let's just see what product of posets is. So if P and Q are two posets which are locally finite, then the poset P cross Q is defined as its elements are the elements of the Cartesian product of P and Q in this order P comma Q. Okay. And now two elements of P cross Q, let's say ST and S prime T prime, then they are comparable if and only if comparable and S is less than equal to S prime T prime, if and only if S is less than equal to S prime in the poset T and T is less than equal to T prime in the poset Q. If any one of them, if any one of the pairs S, S prime or T, T prime becomes incomparable, then the pair ST, S prime, T prime is incomparable. Okay.
Yes, ma'am.
So the pair ST is comparable with S prime T prime only when S and S prime are comparable, T, T prime are comparable. Furthermore, ST is less than equal to S prime T prime if and only if this happens. Even if let's say S happens to be less than equal to S prime, but T prime, T is greater than equal to T prime, you do not have an order on. These are incomparable.
Yes, ma'am.
Okay. So once we understand what a product poset looks like, Cartesian product, then for two elements ST less than equal to S prime T prime and PQ, why you have to assume this again? Now you're working in the int of P cross Q.
Okay, ma'am.
Okay. So this interval ST comma S prime T prime makes sense only with this inequality, right? So then the Mobius function of the poset P cross Q is defined by the product of the Mobius functions, individual Mobius functions. So mu of P cross Q on the element ST S prime T prime is equal to the product of mu P S S prime mu Q T T prime. Okay.
Okay, ma'am.
And maybe I can show a few examples in the book itself. Or no, it's okay. I mean, it's okay. You can read this up, or if you people want, let me know in the. I will put up a write up for this.
Okay, ma'am.
Okay. So yeah, this is what I wanted to cover.
Okay,
And
ma'am.
just one topic which we need to see now is the lattices and their Mobius functions. So far, we have seen posets and their Mobius functions. We will now see lattices and their Mobius functions, which actually is the heading of this unit. So yeah, but a lot of build-up was needed. So that is okay.
Okay, ma'am.
So this we will see tomorrow, and in the next week we'll shift back to generating functionology. Okay, and we'll see WZ pairs and other things there.
Okay, ma'am. For the NSEM, it will be the whole syllabus, right? From the
Yeah, yeah,
beginning.
yeah.
Okay.
Right from the first lecture, and including whatever write-ups you people have been preparing and submitting as part of assignments.
Yes,
Everything
ma'am.
which we have touched upon.
Okay, ma'am.
Okay. Anything else?
No, ma'am.
Okay. So if at all you get to talk to uh, Ridhiman, you can ask him also that this is okay. This anyway got recorded, so he would know if he sees the lecture.
Yes,
Otherwise,
ma'am.
I don't know.
Yeah.
It's okay. Okay, chalo. See you tomorrow then.
Okay, ma'am. Bye, ma'am.
Bye.